equations ax equals b or ax equals y, however you actually try to frame it. And this is basically your unknowns. This is a known matrix of coefficients. And this is your output vector. So unknowns or input, or this is your output vector, or again, solution space. You can say this is unknown. Generally, this is your input vector. That's how we use the terminologies when we try to find the unknowns or solve for the unknowns using the system of equations. So we actually covered Gaussian elimination technique. That's the very first thing we actually did. Gaussian elimination, and we actually learned it with partial pivoting. Then we actually looked at LU decomposition, where we try to decompose the system of equations, or basically decompose A as L times U, and rewriting that equation, basically AX equals B. I can write it as LU times X equals to B. I substitute UX as Y, so LY equals B. So solve for Y first. And once you solve for Y first using forward substitution, and then once you get Y, you basically solve for X using back substitution. So that's what we covered so far during our lectures earlier. So today what we are going to do is just extension of what we were discussing. So in LU decomposition, we're basically trying to we are basically trying to decompose this matrix A into L and U. L basically is lower triangular and U basically means upper triangular. So L11, all zeros, L21, L22, and so on, Ln. And this has got all the entries in the lower triangle. Everything else is zeros. Okay, so this is a lower triangular matrix. And similarly, let me see. We have U's, and U's is all upper triangular. So you have U11, U22 diagonal entries. This is n cross n. This is n cross n. And you have all the entries above the diagonal. And all the entries below the diagonals are zero. So that is your upper triangular matrix. Is everybody with me so far? I love Pakistan. I will sacrifice my life for Pakistan. So if you are playing a video or something, please do not turn your mic on, because it actually affects the whole class. So please, if you are using music or listening to any other stream, video stream, please do not put your mic on, or please mute yourself. Okay, so having got your lower triangular matrix and upper triangular matrix, then we actually solve for the unknown X here. Now there are some situations, it's okay. So we also discussed how to get this lower triangular matrix and upper triangular matrix. So if you put all the diagonals to be 1 for the lower triangular matrix, we actually got Doolittle's algorithm. Doolittle algorithm basically means all diagonal entries of your L matrix is forced to be ones, and then you solve for the unknowns in the U and L matrix, solve for unknown coefficients. In L and U matrix. So that was Doolittle algorithm. And similarly, we have Crowd's algorithm. In the Crowd's algorithm, what we did, we actually enforce these diagonal entries of U to be 1, and then we solve for the unknown coefficients. Okay. So one specific instance that generally happens in physical system is this A matrix turns out to be symmetric and positive definite. Symmetric and positive definite. So what a positive definite means that determinant of A is greater than 0. Is greater than 0. And symmetric basically means A is equals to A transpose. Transpose basically means we transpose the rows into columns and columns into rows. So if we do that, for example, if I take this matrix 2, 1, 3, so let's say this is my A matrix. Now, is this matrix symmetric?
Yes.
Yeah?
No.
No? So what will be A transpose? Can somebody tell me what will be A transpose? Let me actually ask a student from the class here. Okay, how about Payam?
Yes, Professor.
So can you tell me what will be the elements of A transpose?
Okay, so it's going to be 7.
A transpose. So when you say transpose, transpose basically means the rows will become column and column will become rows. That's it.
Oh, sorry. Okay, so it's going to be 3.
No. So
Rows become columns.
if row and put it in a column and this column becomes row, what do I get as the first entry?
So it's going to be 3, 1, 2.
Okay, let me actually write here. So 3, 1, 2, that's what you're saying?
Yes.
So when you're doing 3, 1, 2, what is happening that 3, 1, 2 is appearing nowhere. It is basically, you are basically reading from the reverse order. That's not what we are doing. What we are doing, we are taking this entry 2, 1, and making it into a column, which will be 2, 1, and 3.
Okay, from left side. Okay.
Yeah. And similarly, if I take this and put it in a reverse, the column format, I will get 4, -1. And this row will become column. So if I do that, you actually see the matrix remains the same. Is everybody with me?
Right.
Right? Is everybody with me in the class?
Yes.
Yeah.
Yeah. So that is what we call a symmetric matrix. So basically A and A transpose are just the same. They are exactly basically mirror image of each other. So if you actually take the diagonal, basically you see along after the diagonal is basically a mirror line, and all the entries which are equidistant from the diagonal are basically the same. Do you see what I'm saying here? So this is a diagonal entry, equidistant from the diagonal are the same. So that's what basically happening. So that is what your A transpose or symmetric A matrix basically means. Can somebody quickly find out what is the determinant of A? You don't have to calculate, you can use MATLAB. You just type the matrix A and then say determinant, you just will get the determinant of A, DET A, that should work, I hope. And you can also calculate it. It will be easy to calculate actually. 2, 8 minus 1 minus 1, 2 plus 3 plus 3, -1, -12. So it will be 8 minus 1, 7, 14, -1, 5, -5, minus 13, that minus 39. So it will be 14, 39, 5, 44, and it should be 30 negative. Is that?
Minus 30, yes.
That's what you're getting. That's good. So basically you see this determinant is now -30, which is not greater than z, it is less than 0. So this is not positive definite. So this matrix is not positive definite. Is everybody with me so far?
Yes.
Yeah.
Yeah.
Okay. Now, if I would have uh, got A matrix as positive definite, then what would I have seen that A, which is written as L times U, and A transpose would be U transpose L transpose. So when you actually take the transpose of the combination of matrices, it actually changes its order. So L, if you take the transpose of this, it will give me an A becomes A transpose. But if you take the transpose of this, which are multiplication of two matrices, if you take the transpose of that, what will happen? The U will actually comes, I mean, the order will change. The U matrix will come first with the transpose sign, and L matrix will come in the last with the transpose sign. Is it okay with me? Yeah. Are you with me, guys?
Yes.
Yes.
Yes, well.
Yeah.
Good. So if I have got a symmetric and positive definite, now this specific case I have got as not positive definite. I'm just seeing what element should I change to make it positive definite. So if I
Three.
I'm sorry.
-3. That can do it.
No, that's not also helping because -3 will come over here and it will change. So, okay. Just give me a second. I'm just thinking of how to make that as a positive definite. Which element should I change so that I get a positive definite here? -3. Okay, how about I'm changing this A matrix as a new 2, 1, 3, 1, 2, 2, 3, 2, 1. Can you kindly find the determinant here quickly and let me know if whether I'm getting a positive definite or not?
I got a -11.
Okay, so I need to basically pick an example from the textbook to get a positive definite rather than making up numbers here. Just give me a second. Let me actually pick a matrix which is positive definite. Okay. Okay, so the number I am basically looking at is example 1121, and you can see it has got, okay, from 1121, let me actually write that matrix here. That matrix, whether it is actually positive definite or not. -5, -3, -5, and eating. Can you check whether what's the determinant you are getting? This is example 11.21. I'm not reading the chats. Just give me a second. Yeah. 1296. Okay. So, okay, so Michael was also suggesting something. I had missed that, sorry. So, okay, so you actually get this matrix, which is having, which is symmetric, and as it is symmetric and positive definite. Positive definite basically means that determinant of A is greater than 0. The reason we need this specific property because we will see that in many physical systems, like if you have solving a finite element method, we are solving force is equals to K times X. So this is a stiffness matrix. So stiffness matrix by nature is basically symmetric and positive definite. So there are many systems or many physical systems where you will find that the matrices that you are observing from physical properties has to be symmetric and positive definite. So, and that for this specific class of matrices, what happens that when you actually do the transpose and you know that A transpose is equals to A and is equals to L times U. So what you actually see that the LU decomposition will just becomes A equals L times L transpose. So you will see that L is equals to U transpose, and which actually also means that U matrix is L transpose. So A is equals to L times U basically means L times L transpose. So the advantage of this is that you would have less number of unknown coefficients to determine. Basically, you need to consider only the L matrix here. So if you are looking at this in a generic matrix where it is not symmetric and positive definite, you will see that L and U have different elements. So L matrix has different elements here. So it has got around six. If it is a 3 by 3 matrix, it has got 6. And similarly, it has got another 6 on the upper a triangular matrix form. So you have more number of unknowns to be determined. But if you actually have this specific situation where it is symmetric and positive definite, then A or LU decomposition becomes a bit more easier because now U matrix is just the transpose of your lower triangular matrix. So this is what we call as Cholesky factorization. And this type of factorization has a specific name and it is called as Cholesky factorization. Is everybody with me so far?
Yeah.
And how to decompose this specific matrix into L transpose? If you really, if you actually know in your code that this is symmetric and positive definite, then I just need zero, 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 L12, L13, L23. Okay, so I am, let me call that as L21. So this is L21 and L31, L32. Okay. So L11, I just was basically trying to make the system consistent or make these notations consistent. So what I'm saying, the first index is the row, second index is the column. So L11 means basically first row, first column entry. L21 basically means second row, first column entry, third row, first column entry, 3, 1, 3, 2, 3, 3, likewise. Now, since it is symmetric and positive definite, the U matrix, this is your L matrix, normal L matrix, and this is your U matrix. Now, U matrix, I know it is nothing, but it is just a transpose of L. So this L basically gets transposed, and this is my U matrix. So L11, L22, L33 remain same, and L21 now goes above the diagonal, L31 now goes above the diagonal, L32 goes above the diagonal, and these will become 0. Is everybody with me so far?
Yeah, I follow.
Yes, I follow.
Yeah. Any questions from you guys if you are not following it?
Can you repeat the multiplication again, please?
Just come again, sorry.
What you said earlier.
what I said earlier. So what I was basically saying that if your matrix is symmetric and positive definite, then LU decomposition becomes equals to L times L transpose, which is also called as Cholesky factorization. So I have got L matrix and the U matrix is a transpose of my L matrix. So actually, right, let me actually use a separate sheet and so I have got A matrix, which is 9, 6, -3, 6, 13, -5, -3, -5, and 18. And if I have to do it LU decomposition, which is lower triangular and upper triangular, just because this is a symmetric and my determinant of A is greater than 0, that means it is a positive definite as well. So it is positive definite and it is symmetric. So if that is the case, then LU decomposition becomes L times L transpose because U is just equals to L transpose. Is everybody with me so far? And that's what we actually see: L11, L21, L31, L22, 0, 0, 0, L32, L33. This is L matrix, and my U matrix will be the same matrix in transposed form. So in transposed form, it will be L11, L21 will go above the diagonal. That this column becomes a row. L22 will remain the same. Zeros will come at the bottom. L32 and L33. Is everybody with me so far? Now let's actually find the elements of the matrices, how to find the elements. So I have got how many unknowns? 1, 2, 3, 4, 5, 6. I have got 6 unknowns here. Yeah.
Yes.
Yeah.
Yeah. And how many equations I have got? I mean, how many entries I have got here? Can somebody tell me? Can somebody?
9.
9. So how can you solve 6 unknowns for only 9 entries? I mean, you have more entries and you have less variables, right? Am I correct?
Yes.
So can somebody volunteer and say what is happening? Why is it happening here? What is?
Okay, so we are going to force one of the diagonal to be 1.
No, here we are not doing that. So
Oh, no.
factorization here, we are not the Cholesky factorization. We are not doing that, forcing any diagonal entry to be 1. So we are not doing that. No diagonal entries being forced to 1. So if I have to find these coefficients, how will I, what's happening? What is the problem here? Or what is the scenario? Okay, so Kyle says because it is symmetry, we can eliminate 3 values, which is perfect. That's what it is. So if you look at this, this is symmetric matrix. So it actually has only 6 independent numbers. It has got diagonal numbers 1, 2, and 3, 4, 5, and 6. The other 3 values are just the same. So they are not different. Are you seeing what I'm saying here? So if matrix is symmetric, so these entries do not make any difference because they are just the same. That is what I'm getting below the diagonal as well. So I'm not going to get any new numbers over here or new equations over here. So because it is symmetric, I have got I have got 6 independent values and I have got 6 independent values or variables over here. I just need to equate these matrices and find the solve for these unknowns. So let me actually do that. So first I need to do the multiplication of these matrices. So I will get L11 square. Then I will got L11 times L21. Then this will multiply by that. It will get L11 times L31. So similarly, the bottom, this will be L21 times L11. This will be L21 square plus L22 square. And correct me if I'm wrong. I'm just multiplying it. If you see I'm making some mistake, please correct me. Plus L22 times L32. This will be L31 times L11. This will be L31 times L21 plus L32 L2 times L22, and this will be L31 square plus L32 square plus L33 square. Am I correct, guys? I just multiplied this matrix with this. That's what I'm getting. Are you with me, guys?
Yes, looks good.
Yeah, just trying to check it.
I would appreciate feedback, guys.
Yeah, it looks good.
That
It looks good. Just finished checking
It
it.
just took me a while to write it down and then check.
Okay, so now once we have got this, now we know that this matrix has to be the same as this matrix. So all the coefficients have to be equated. I mean, corresponding coefficients have to be same. So L11 square will be 9, and we are taking just positive square root. So L11 is equals to 3. Now L11 times L21 is equals to 6. L11 has already been found out. So L21 is 6 divided by 3, which is 2. L11 times L31 is negative 3. I already know L11, so L31 would be negative 3 divided by 3 will be negative 1. So I've got the first row, basically L11, L21, L31. Now this one, L21 already solved, so I don't need to check again. L21 square plus L2 square is equals to 13. And I know L21 square, L21 basically is 2. So L22 square is 13 minus 4, which is 9. And L22 is again comes out to be 3. So L22 is gone. Now we are basically solving this. So here L22 is known, L31 is known, and L32 is not known. So let's solve for L32. So L21 is known, L31 is known, L22 is known, L32 is not known, and that has to be equals to negative 5. So L21 is 2 times L31, which is negative 1, plus L22, which is 3 times L32, which is not known. And if you solve for that, how much you will get? L32 is negative 5, negative 3 by 3 is equals to negative 1. Okay, and then I know L31, I know L32, the only thing remaining is L33. So L33 is L31 square plus L32 square plus L33 square, that has to be equals to 18, and L31 is negative 1, L32 is negative 1, so 1 plus 1, 2. So L33 square is equals to 16, and L33 comes out to be 4. So now if I actually basically construct my, so I know all the elements of L matrix. So L matrix looks like this: 3, 0, 0, 2, L22 is 3, 0, L31 is negative 1, L32 is negative 1, and L33 is 4. That is my L matrix.
Professor, I have a
Yeah.
question.
Yeah.
Why do you take only the positive value when you take the square root?
So the reason is that it is a positive definite, and the diagonal entries have to be positive. It cannot be negative.
Okay, thank you.
Okay. So diagonal entries cannot be negative. So it has to be positive for positive definite matrix. So that is what basically you are actually getting L matrix as this. Now, if you multiply this with its transpose, I mean, U matrix is the transpose of this, which is 3, 2, negative 1, 0, 0, 3, negative 1, 0, and 4. So it is just transpose. And if you multiply these two matrices, that what you will get is a matrix. So you can multiply that and check and let me know if you are getting it or not. I mean, if you have a MATLAB open in front of you, you can quickly multiply that and let me know if you're getting this.
Yeah, I confirmed I got the same matrix we started out with if you do L times L transpose.
Yeah, that's what we actually needed. So we actually got a lower triangular matrix and upper triangular matrix, and that's basically basically it means that you have less number of equations for your unknown coefficients. If you have a symmetric and positive definite, you don't need to use U's and separately, because in that case, if A is symmetric and positive definite, then you know the U matrix is a transpose of L. And instead of solving for 9 equations, I am now solving for only 6 equations: 1, 2, 3, 4, 5, and 6. Is everybody with me so far?
Yeah.
And questions, guys?
So all we were doing just to verify was just multiplying L times L transpose just to verify.
Yeah. We just verify that whatever we are getting is correct or not. So the reason I'm doing this for you, one of the last time in the last class, somebody asked me, okay, can I give an example and solve it? So it will basically addressing that part. And second thing is, once you get an L and U basically somebody asks you to do the decomposition and you got this matrices. Now you will ask me, okay, why you are not posting the solution for your problem? So this is what I'm saying. And I've been saying that when you get a solving for numerical methods, there are ways you can check whether the solution is correct or not. So you get the solution, you multiply that, and if you get this matrix, that means the solution is correct. There's nobody, if somebody tells you that this is not a solution, that person is wrong. You are actually correct. So you have to check your own solutions. Make sense?
Yes.
If you not agree, you are welcome to give your feedback. Are you with me, guys?
Yes.
Yeah, I follow you.
Okay. So this is what we are doing with LU decomposition and Cholesky factorization. So we switch our discussion now for the cases that we were seeing in the last lecture, that if we have more number of equations or more number of unknowns, how to solve for that. So far what we are doing, this is n cross n, this is n cross 1, this is n cross 1. So this is basically, we are always starting with a square matrix. That's what we have been doing. LU decomposition or Cholesky factorization or Gaussian elimination. These techniques actually work when you have a square matrix. What will happen if the matrix is not square? For example, let's say you have this given system of equations. So you have 3 cross 1. Basically, you have 3 by 3, not 3 cross 3. Basically, you have 3 by 3 A matrix. It should not be 3 cross 3. It should be 3 cross 2. So forget about the last row. Oh, sorry, last column. So you have 3 cross 2, 2 cross 1, and 3 cross 1. So you have this system of equations. So if I'm not basically making up any numbers because I don't have equations in front of me, I'm just saying that, okay, let me assume a generic number or generic set of equation where I have this A11 x1 plus A12 x2 is equals to B1, A21 x1 plus A22 x2 is equals to B2. A31 x1 plus A32 x2 is equals to B3. I have these equations, set of equations. So these are three equations and I have two unknowns. Three equations and I have only two unknowns. So how do we solve for that? How do we solve for x1 and x2? Can we solve, first of all, can we solve for it? And how can we solve for it? So any idea, guys?
Can we make it a square by filling the matrix?
So no, we cannot fill in any matrix here, or we cannot make it square, because this is what you actually get. This is the system of equations. If you change any system of equations, you cannot just arbitrarily say any, I mean, you cannot arbitrarily bring in any numbers or any value. So this is what you actually get. You're not allowed to change the composition of this matrix. You're not allowed to change the number of variables. You're not allowed to change this measure, this output vector. Now let me actually discuss or describe what you actually, how in physically, how, where do you see this type of system? So for example, you have the data points. You are working in a Cartesian coordinate system, X and Y. Okay, and you have got three data points. Let's say you have got X1, let me call that as B1. I have got X2, B2, and I have got X3, B3. I have got 3 points, for example. And I want to pass a straight line through this. I'm just trying to fit a line. So just imagine that I want to fit a straight line through them. Straight line. And it need not be 3, it can be 4, 5, 6, it can be any number of rows you can have. So fit a straight line through, let's say 3 data points, because I have 3, I only wrote 3 rows, so 3 data points. So here you see that the equation of a straight line is y is equals to m times x plus c. Everybody agrees with me? Yeah?
Yeah.
Yeah. And where m and c are your unknowns, which are basically these are the two unknowns. These are basically unknown slope and unknown intercept. And this is unknown intercept. And I want to pass a line such that it fits the data points. Fits the data points means it is equidistant from all the data points. So somehow the line should fit that. Fit the sense it is not like it should pass through this, so it just pass through this. You can have a line which passes through this, but then it will be very, very deep away from this data point. So what is the best line that actually fits through these data points? So that is what the general fitting problem, data fitting problem happens. And it need not be a straight line, it can be polynomial, it can be any other function. But at this point, we are basically trying to fit a straight line through number of data points. And I have got more data points because if I have only got 2 data points, I know I can fit a straight line. It is a square system, square matrix, and 2 by 2 matrix, 2 unknowns, and you can fit a straight line through that. But if you have got more measurements means B1, B2, or B3, more data points, then what will be my unknown slope and unknown? How do I actually solve for that? So let me actually mention what are A matrix and what is X matrix and what is B matrix, and how can I frame or rephrase this specific problem in this specific form. So my unknowns are M and C. So what I'm trying to do is, I know my data points B1, B2, and B3, and I know for these specific X1 and X2 and X3. So what is happening here, that if I write it like this, does that make sense to you?
Yes.
So I'm giving couple of minutes to the class to see whether this specific representation makes sense. So in basically what I'm trying to say here, I want to find a slope and intercept. These are my unknowns. And these are my A matrix because this is known. X1 is this coefficient is known. So if I just take some numbers here, I mean, I hope you are understanding what I'm trying to say. These are not variables, these are unknown numbers. So let's say I have got 2, 3, 3, 5, and let's say 7, 6. So these are the data points I got. So I know X1, I know B1. B1 is basically the corresponding coordinate in the y-axis. So I got this coordinate, I got this coordinate. I want to fit a straight line through these data points such that the line actually tries to minimize the distance between each data point. So what I'm saying here, that if I want to fit a straight line such that it satisfies this straight line equation. So if you multiply this row with this column, you actually get this. C times M x1 is equals to B1. First, the second row multiplication will give you C plus mx2 is equals to B2. Third row will give you C plus mx3 is equals to B3. Isn't it? Is everybody following it, what I'm saying?
Professor?
Yeah.
Is there any reason you put C first and then M? So if I inverse M and C, then the X in one row will be they switch?
Yes, they will switch. Because then multiplication has to be, slope has to multiply with the X. That's why 1 is there and C is here. But otherwise, if you switch M and C at top, then X1 will be at the beginning and 1 will come at these columns will interchange. So what actually, I believe it was Koi from the voice. So you can write the same matrix like this form, but then your unknowns will be written as like this.
Yeah, so my question is, do you have to write in C first and then M?
No. There is no such requirement. The order of the variables will change if you change the columns. You can write A matrix like this as well. Are you guys with me so far or not?
Yes.
Yeah.
So the purpose of this is you try to find a straight line that's closer to 3 points.
Yeah. It can be 3, it can be 4, it can be 5. So if it is 4 points, then I have another row for A matrix. If it is 5 points, I have another row for this matrix. So this matrix will keep on growing depending on how many data points you have. So right now I am using only 3 data points. I have 3 cross 1. If you have 5 data points, it will be 5 cross 1. If there's 10 data points, at 10 cross 1. So this matrix will keep on changing. And this is a known matrix. This is what you know, the data points are known to you. So this is what we are expecting A matrix. The number of unknowns remain only 2 because this for straight line only these are the 2 unknowns. So I am just having the 2 unknowns. I have got more equations. Now I've got 3 equations to solve for 2 unknowns.
Okay, thank you.
You see what I'm saying?
No, thank you.
Yeah, thanks. And similarly, when you have 5 data points in this A matrix, the Y vector will increase. So the only unknowns, the here will remain the same. They are not going to change. But your measurements, which use data points here, B1, B2, B3, and this A matrix will keep on changing, will keep on increasing the size. So this is the exact scenario which I was saying, that you have more number of equations, less number of unknowns. So in that scenario, what you actually do the least square solution. Least square solution says that I cannot fit a straight line, or I cannot uniquely solve for C and M. I cannot uniquely find a line which passes through this point and this point and this point together. So it cannot be one line that passes through all these data points. So there cannot be one line, or there cannot be one value of slope that passes through all the lines. So what will happen, that there will be a line that actually fits best, but then what I do, I see the distance between these lines and try to minimize that. That is the error I will have. So I want to minimize the error. So let's say this is error E1, this is E2, E3. So the error E1 is Y1 minus B1. E2 is Y2 minus B2. What is Y1? Y1 is M times X1 plus C. That is Y1 minus B1. What is Y2? Y2 is given by your straight line equation, plus C minus B2. What is error 3? Error 3 is Y3 minus B3. This is M times X3 plus C minus B3. That is your error. Now, least square solution says that you minimize the sum of the square of the errors. Minimize the sum of the square of the errors. So what it is saying, that if the error is given by vector R, and then you actually take the square root of E1 square plus E2 square plus E3 square, and you minimize that, that is what your solution would be. And the solution basically is given by, the least square solution is given by A transpose A inverse A transpose Y. This is a very, very important solution. I'm not going into a derivation that how do you actually from here, how do you actually go into finding this least square solution. But you can look at the derivation. I can show you the derivation if somebody is interested to know what, how do you actually get this. So I can basically show that or share that derivation. We are not interested at this point of derivation of how you actually get this, but the formulation or the basic concept is this. So you try to minimize the error between the straight line and the data point. So the straight line data points E1. E1 is actually, actual data point is B1, but what I am getting using straight line, my value at corresponding X1 is M times X1 plus C. So this is the error that I will have for the first data point. This is the error I will have for the second data point. This is the error I will have for the third data point. And you square it, add it, and minimize that sum square root of the sum of the squares. So minimize the sum of the squares of the errors. That's what you actually get. Now, what is X least square solution? What is X here? X is your unknown vector.
Professor, what's the letter next to the square equation?
Sorry, come again.
What's that variable on the left side of the square root?
This one. This is R, residual vector. We call that as a residual vector, R. It is basically square root of the sum of the squares. Derivation also does not exist in a textbook. I will share the derivation with you in the beach board. But what we are doing here, this is a matrix A, which is your known, all the data points that are known to you, that is considered like that. This is basically your unknowns, and this is your, again, the known measurement data points. And what we are trying to solve is this unknown vector. How can we solve for this unknown vector? And the method for that is you do a least square solution for it. And the least square solution says that you can solve for this unknown using this formula. And this formula is very, very, very important formula. You will find in many, many applications, whether it is economics, whether it's statistics, whether it is electrical engineering, whether it is chemical engineering, whether it is mechanical engineering. If you have this type of data points or measurements, or you're dealing with this type of systems where you are basically trying to solve the system of equations, where many number of equations but less number of unknowns, this is the go-to solution for that specific case scenario. Now let's see how we can how basically the dimensions and the dimensions of the matrices actually match and work here. So A transpose, A is my 3 cross 1. So what is the dimension of A transpose? A transpose would be, this will be that rows will come columns, columns becomes rows. So A transpose will be 1 cross 3. A becomes 3 cross 1. And if you multiply these two matrices, the one, basically what you are getting is 1 cross 1 as an output. And you take the inverse, it will be just a reciprocal of that. And then you have A transpose, again, it is 1 cross 3. Actually, it is 3 cross 2. So 2 cross 3, 3 cross 2, you got 2 cross 2, I mean 2 by 2 matrices. And then A transpose is 2 cross 3. So 2 cross 2 times 2 cross 3 will becomes 2 cross 3. Y is 3 cross 1. So when you solve for that, you will get 2 cross 1. So your X least squared is basically going to be 2 cross 1, basically 2 rows or 2 entries. And that is what we are solving for, M and C, or C and M. So I can actually share the MATLAB code. Actually, we do not have the time to go through the code step by step. What I will do, I will share this specific code with you guys. Just give me a second here. Okay, so this is specific least square solution code. Here I have these data points. I hope this screen is visible on your desktop, right?
Yeah, I can see it.
Okay, so what I did, I just basically code the same things that we are doing, same system of equations. We have data points here, 1, 3, signal here. Just give me a second, guys. I'm trying to reconnect to my desktop. I'm still trying to connect it.
Professor, can I have a question?
Go ahead.
The solution you find with the least square method, are they all on the same line, the line that you draw with the least error, right?
Sorry, come again. What is the question?
The solution from the least square method, they will be on the same line, right? The points.
Which one you're talking about?
So this solution, they all are lie on the same line, right? On the graph that you draw.
This one?
Yeah. So the solution will be.
No, hold on. So this is basically a line that is given by this equation, y equals mx plus c. Now, if you know the slope and you know the intercept, then for each value of x, you get a corresponding value of y using this equation, which is basically the point on this line. So point on this line is y1, point on this line is y2, point on this line is y3. And how do I get these values? I get these values using this equation where I plug in the value of x1 over there. I plug in x1 over here, I get y1. I plug in x2 value over this equation, I got y2. I plug in x3 value in this equation, I got y3. Now the actual value is not y3, actual value is b3, actual value is b2, actual value is b1. And that is why there is an error for each data point, because my line does not go through these data points. It basically tries to fit as best as possible. Did I answer your question?
I don't understand what is the XLS. Is that the X, the solution you're trying to find?
Yeah, the solution I'm trying to find, and my X basically are this C and M, and in this scenario.
Okay.
So this X least square, this is my least square solution. This is basically representing my unknowns. So this is my X vector. Generally, when I say A, X equals B, instead of this is representing X here, this is your X vector, unknown. And the solution for that is given by this.
Okay, so that is the slope and intercept of the line you draw, right?
Yes, yes.
Okay, okay, got it.
Okay, so I got my connection back.
I have another question.
Go ahead.
This one apply for equation. No, the number of the equation more than the unknown. But if the unknown more than more than number of the equation, so can we use this?
We can use not this formulation. I would actually would have liked to discuss that and cover that in today's lecture, but I don't think we can cover it. We will take it in the next lecture. So what I was basically showing you is only when we have more number of equations. The next lecture, I will actually start with when we have less number of equations and more number of unknowns, how to solve that.
Okay, thank you.
Okay, so here, can you see this screen, by the way, in your desktop, guys?
Yes, I do see
Yeah,
it.
Okay, so let me run this quickly before it again closes on. So here you actually see the data points. This is the first data point, the second data point, this is the third data point. And this is a straight line that actually is obtained by solving that least square solution. So let me actually go through the code and you will actually see how we are doing that. So we have got 3 data points, 1 and 2, which is my x coordinate, y coordinate, and 3 and 5 and 7 and 6. It need not be these numbers. I can basically increase it to some other number as well. So let's say I have 4 and 10 as well. So these are, you can have as many number of equations as you like. So as many number of data points you like. Now, if I increase the number of data points, I am basically changing my A matrix as well. A matrix is constructed out of that data points, right? Remember guys, if you have your notes, if you have taken that notes, then you probably have seen that A matrix is 1 and x coordinate, 1 and x coordinate, second coordinate, 1 and third coordinate. And since I increase the data point, so I will have another row for the fourth data point that I just added. Is everybody following so far with me?
yeah,
Yeah.
So y vec is basically your b vector and least square solution where it is A transpose in MATLAB you will basically say is A dash, which is A transpose times A, and you take the inverse of that. So A transpose A inverse times A transpose, again A transpose times your b vector, which is y vector. I'm calling that as y vector at this point of time. So once you get this least square solution, which is basically your M and C, then you can find the corresponding y's using this specific formulation. And if I run this again, so you see the fourth data point is actually plotting over here and the line has shifted. Are you with me so far?
yeah,
Yes.
Saying that as you keep on changing the data points, it is trying to fit a straight line that best tries to minimize the error between the data points. So this is the line which tries to minimize the error between 4 data points. I can increase to 5, 6, and 7, and depending on how many number of equations I have, I can always solve for two of the unknowns. And 2 unknowns are my slope and intercept, which is given by this x least square. So if I actually show you the output of that, it has got only 2 values, the intercept and the slope. Since I have 1 on the beginning, so this is the first is C and second is M, the slope. If I keep on changing this, so let's say I change it to 5 and run it again, you see now the data points have shifted and the line has also shifted. It tries to best fit the data points. Does it make sense, guys?
yeah.
Yes, it makes sense.
Any questions so far?
Is this like I remember doing it in high school. Is this like the matrix version of like Newton methods for linear approximation, or it's like completely different?
Come again. I miss your point. Can you ask your question again?
Is this the same as the Newton linear approximation, just like matrix form, or it's different?
It's not a linear approximation. It is basically trying to find a least square solution, which is trying to minimize the residual vector, minimize the error between the knowns and your approximation. So it is not a linearization or linear approximation. It is trying to, because here, if I actually go back and share my desktop or share the document camera again, okay, so here I have started with only straight line equation. What if it is not a straight line equation? What if I say that I want it using a polynomial? Let's say I want a polynomial of a naught plus a1 x square plus a2 x cube. I want to fit, sorry, a1x plus a2x square. I want to fit a square or quadratic polynomial through the data points. So if I have 3 data points, then I can fit exactly a quadratic because I have 3 unknown coefficients. So I have 3 data points, 3 unknown coefficients, a square matrix. But if I have more number of data points, I want to fit a quadratic polynomial, I can still solve for a0, a1, and a2 using this least square approximation. Okay.
So that will just increase, I guess, the variables, but we can say.
Yeah. So we will discuss more. Actually, we don't have much time today to actually go through the discussion about these solutions, but we will discuss about it more in the next lecture. And we will also see the case when we have less number of equations and more number of unknowns. We will also see that case. Okay. Okay, guys. So if there are no other questions, we will wrap today's discussion and I will see you in the next lecture.
Thank you, Professor.
Thank you.
Yeah.
Professor, I have a question really quick.
Yeah, go ahead.
Can I just quickly look at what was I think it was your MATLAB code. Just what was that stuff at the bottom? I'm just interested about the MATLAB itself, like the code.
Yeah,
Is that just figure stuff?
I will post this code in the beach board. Just
Oh, okay.
No issues.
Perfect. Okay, thank you.
Any other questions, guys?
I think I have a question. So is this solution unique? So only one solution?
Yeah, it is the best possible solution which minimizes the error. It is the best possible solution.
Okay, thank you.
There is no other solution which can minimize the error as best as this one. So
Professor?
Unique solution, but you get a solution which minimizes the error. So we are always basically doing the minimization of my errors. So this is the what we are basically doing. So there is no unique solution because you cannot fit a straight line which goes through all 3 data points, right?
Yeah.
So there cannot be a unique solution in this scenario because you cannot pass a line which can fit through all 3 data points which are lying in space arbitrarily.
So it's just the best method to minimize the error.
Yes, yes.
Okay.
I have a question about a homework.
Okay, go ahead.
So you meant, okay, so I have 3 MATLAB program for, the 3 different methods. So I have to plot, and you want some common regarding the result or the relationship between you and the temperature?
No, the relationship is already given. So I don't want you to find any other another relationship. We just need to see how different methods are giving you different solutions for the same problem.
Oh, okay. So you want discussion regarding like, okay, what's the different method, what's the pro and con, and
yes,
how fast they're approaching and how
yes,
accurate, right? Okay.
Yes.
Thank you, sir.
Yes.
Professor?
Yeah.
Yeah, for plotting, are we supposed to use the set of data that we get and plot it in like Excel and then write it in code to MATLAB, or are we supposed to use Excel to plot it?
You can do whatever plot. You can do Excel. You can do MATLAB. Whatever is convenient. That's fine.
And in the problem, because we didn't get a set interval, I just used my own, and for my secant was slower than my my bisect, but I did my explanation about why it was slower than my bisect after like after 25. Is that good enough, or should I change the set point so it would show that the secant is faster than the bisect?
No, that's fine. Whatever you have chosen the data points, that should be okay.
Okay, thank you.
Professor, I have a question.
Go ahead.
I already submitted the homework. If I want to add something, and can I do a resubmission?
Yes, you can do that resubmission.
Okay, thanks.
Yeah. Okay, guys, I'm stopping this and we'll see you in the next lecture.